Hi, everyone. So welcome back to the second session. And you're right, a lot of you also pointed out that a tree cannot be the edge graph of a polyhedron. That's absolutely correct. Also, in fact, there's a characterization of which graphs, planar graphs, are the edge graphs of some convex polyhedron, something like a sphere that's topologically a sphere. So there's a characterization of that in terms of, connectivity of the graph, and you delete vertices and edges. That's called Steinitz's theorem. But as I said, there's an unsolved problem. I mean, what happens when you look at with polyhedra which are not convex, not a sphere, let's say, and so then it's not clear what graphs are edge graphs of polyhedron. If there's some kind of graph theoretic characterization.
Sir, what is this convex polyhedra? What is the meaning of a convex polyhedra? What is convex?
So convex polyhedra is the sort of thing that you are already familiar with, things like a tetrahedron, a cube, etc. So these are convex objects on the in R3 in the space we live in, because these are convex. Because convex in Euclidean geometry means that if you take 2 points inside a region and you join them by a straight line, then it remains inside the straight line. Okay, so it's cut out by planes. Okay, and all these, like a cube is cut out by planes, an icosahedron is cut out by planes, and so on. So these are all convex polyhedron, and the kind of thing that we were concerned with, these are also topologically equivalent to a sphere. Okay, so that's a convex polyhedron, but there are others. There's things that I showed you. Maybe this is not part of the lecture notes, but I shared the screen at certain points, and I showed you a picture of a polyhedron which has a hole in the middle. It's like a torus. So now that's not convex, because if you're on one side of the hole and another side of the hole and you draw a straight line, you'll kind of exit your solid object, right? So you kind of exit this region.
Sir, so if you take the torus with the triangle which you showed last time, the torus with the triangle cut out in between, so is that a not convex polyhedra?
So like torus with a triangle.
Sorry. If I draw a torus like polyhedra with a torus, like what do you say, which is topologically the same as a torus.
Yeah, that's not going to be convex. That's right.
And I cut out a triangle there in between.
Yeah, that's right. Yeah, you have to. I mean, it's not just to cut out a triangle. You have to have a sort of a hole through it. Right? So if you cut out a triangle, there'll be edges. We don't want a surface with edges. Yeah, that's right. That's not a convex polyhedron. But let me sort of tell you what we'll start off with. So we'll start off with one of the favorite surfaces and some favorite shapes that sort of a topology student first sees. It is the favorite shapes of a beginning student, and this is a Mobius strip, and I guess all of you have seen in some form or the other. I'll come to that a little bit later and sort of ask you where you've seen it, etc. But what happens is, if you take so let me sort of describe its construction in terms of a diagram. You take a sort of a rectangular strip of paper, and then you do we'll do some kind of half twist. Okay, so if you want to draw it pictorially, it's something like this, right? So sort of, let's say the sort of the backside is some other color. Okay, it's shaded, and when you sort of twist it, so that's a half twist. If this was going up, this is now going down, and then you glue, right? So you glue these sides, and what you get is a Mobius strip, right? So let's do this. So maybe all of you can see. So let's make this. So I'll just cut out. I've got this piece sort of piece of paper with me, but I want a thin strip, so it's easier to sort of twist. So let me do that. So let me mark out the strip that I want to cut. And so a pair of scissors is a kind of a useful tool for a topologist. At least the topologist always carries around a mental pair of scissors as he or she is cutting and gluing all these various spaces in their minds. Okay, so I've got a sort of a long strip of paper now, and so I'm going to, so if you glue straight across without a twist, then what you get is this band, right? This is the usual band. It's a cylinder, okay? So so this is a familiar shape, and a cylinder, as you all know, it's a two sides. It's got this outside, and then it's got this inside, right? So the inner side over here, and so it's a two-sided shape. It's not a closed surface. So in the last time I was talking about the sphere and the torus, etc. These didn't have any boundary edge, but this the cylinder does have boundary, right? So this is one boundary edge over here, and there's another boundary edge over here, right? So that's what a cylinder is. But now what we're interested in is sort of twisting this, right? So this is a sort of a half twist. So we can half twist, and I want to just glue it like this. So I'll have I have some glue here with me. So let me try to do that. So if you place it like this, you just so apply glue on one side of it. Okay. By the way, I encourage whoever has some piece of paper and scissors to do this along with me. So now instead of gluing straight across, I'm going to twist it, do a half twist, and now this part where I'd applied glue sticks with this. Okay. Now this is so now what we get is a Mobius strip. Okay. It's once again, it's a surface with the boundary edge, but this time there's a single boundary edge. Okay, so if you follow this this edge over here, you'll actually sort of traverse, all the edge that's there in this shape. It also has one side. Okay, so if you kind of if you try to color this side, and you continue, you'll find that you've colored the whole thing. Okay, so it's a one-sided surface. So let me actually switch back to the screen and sort of say what topologically how you might be able to sort of represent this. Okay, so by the way, have any of you kind of seen this Mobius strip already in some, some movie or something? Have you seen, the Marvel movies, perhaps? Avengers Endgame. Do you guys know that there's a Mobius strip involved there? But it actually appears in movies as well, okay? And so I guess I shouldn't give away spoilers for Avengers Endgame, which is it's a great movie, I think. But the point is that there's sort of the Mobius strip is involved in time travel, okay? So it turns out that, so when you go back in the past and when you come back, maybe you don't really come back the same place, but you come back in a different orientation. I'll send you some more links to YouTube videos a bit later. But let's look at sort of how you might represent a Mobius strip in terms of a figure. Just like we saw, there was a torus. So last time, let me remind you. So the last time we saw a torus there's a neat way to represent it as a diagram. So you look at this square and you glue opposite sides, right? And these arrows denote, if they're the same arrows, that means they're glued, right? And so so here there's a double arrow, means the top side and the top, and the double arrow on the bottom, they are glued in the same direction. Okay, so if there's a point, let me color, there's another point here, it gets identified with this point. So these two red dots are the same point. Okay, and similarly, so if you have something here, so this green dot is, and this green dot is the same, right? So this is what we saw the last time. So in the Mobius strip, right? So Mobius strip, so a Mobius strip, you can represent as, so here's my rectangular piece of paper that I started with. I just glued one of these sides with the other with a twist. And so this arrow goes the other way around, right now. So I guess, I hope I'm sharing my screen here. Yeah, okay. Right, so that's your, that's the Mobius strip topological. So this time we don't glue the top side to the bottom side. And in fact, so that forms an edge. And if you follow this edge, so let's do that. So let's start somewhere here, and you follow it, and you follow it. And then when you hit this point, well, this point is the same as this point, right? When you remember, this arrow here is identified with this arrow, but going other way. So the bottom of this edge with this arrow on it is the same as this orange dot here. So when you reach this corner over here, that's the same corner as this. So now when you continue along this edge, you go this way, right? And then you reach this point, this corner, that's the same as this corner. And then you continue and you close up, right? So you find that there is indeed, so there's a single boundary edge, right? Okay, so let me sort of list down the properties that we've seen so far. So the properties that we saw, well, just looking at it, physically, is, so one of them is that it's a one-sided surface. So it has a single boundary edge. What else? So here's another property that so it ties up with things we've seen last time. So you can embed K5 on it, okay, which is different from a sphere, right? We saw that last time we proved that you can't embed this complete graph in 5 vertices on a sphere, but you can do so on a torus. So how does that work? So if you look at that, if you look at this torus, okay, here's a picture of how you might embed it. So let's draw like last time. So you do 5 vertices, right? And you want to connect them up. So each pair of vertices should have an edge between them, right? So maybe this connects with that. And now you want to, let's say this, so this edge goes round. Remember that, so in this, so the arrows are, so this is identified with this, right? So although it's going to sort of, this edge is getting identified with upside down edge, the midpoint of it is identified. So if you look at this green edge and it hits this guy at the midpoint, let's assume this is the midpoint, then this continues like this, and that's a closed edge between these two vertices, right? And so we still have something remaining. We have to connect this guy on top here. Let's see, so which one? This one has to be connected with this guy, right? So how do we do that? Well, we can go this way, but this time this point here is identified with this point, so we can sort of continue and and join up, right? And does that finish all the edges that we want? So let's see. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9. Is there one more needed? So 1, 2, 3, 4, 5, 6, 7.
So the bottom left point.
This one and this one, right?
Yeah.
Yeah. So okay. So I guess like this, right? Okay. So that's also. I mean, that you can put in without any trouble. Okay. So that's an embedded K5. Okay. So that's another property. What happens when you cut it into half? Okay. So so let me. Let me put that as a property. So it remains connected. I'll describe it and then I'll say what it exactly means when you cut it in half. Okay, in other words, if let's say I take this, so I look at this Mobius strip here, there's a central line here. Remember that this left endpoint here, this vertex is the same as this vertex. So this forms a closed loop Mobius strip. Now, if I cut it in half along this dotted red line, then what happens is so if you did it on a cylinder, right? If you take a cylinder and then just take a loop going across and then cut it, then you get two pieces, right? But here you still get a single piece, and you can see that in this diagram that we are using. So if you're an ant here, right, and if you cut along this dotted red line, it's still connected, because if you go out, so if you're an ant, you travel and you go here, this edge, remember, is glued to this part over here. So you kind of come out this way, right? So somehow these two, what seems like sort of two pieces on the diagram, they are actually connected when you remember the gluings. Okay, so even after this red line is sort of completely cut off. So we can actually see that happen when we cut our Mobius strips. So let's see that happen. So